first, there are we will start and try to understand infinity in terms of the numbers. Okay, there are other ways of also looking at it, but we will look at it from the numbers perspective. Okay, so what is infinity? Infinity is not one specific number. Okay, it is not one specific thing that like 50, 100 or 5341. It is no number. It is like that is infinite. Okay, it is something which is, because the numbers never end. Okay, the numbers never end, right? You start from 0, let us say 1, 2, 3, 4. You can keep adding 1, 1, 1 and you will get the next number, and there is never a last number, right? Oh God. Okay, I have to switch to my mobile network. Just 1 second. It might take me just 1 second. I will have to start my hotspot. Yo. Okay, I think the net thing is going to get thing. I am going to start my mobile hotspot. Okay, because power is on there. Okay, I'm going to be switching, but I don't see the network. Other networks, let me see. Okay, Z, Y, W, K. Okay, am I audible? Can you hear me?
Yes, sir, I can hear you.
You can hear me, right? Okay, because I've
Yes,
switched the network. So okay, so what we were saying is what kind of a this it becomes, right? I mean, how can we represent and what is infinity? So we will, and there are multiple kinds of infinities. So let me stop sharing. But just to before we sending, you know the natural numbers. Natural numbers, right? Natural numbers are like all positive integers, like starting from 0. 0 is not positive, but 0, 1, and then all the numbers that are come. And then beyond 1, when you go, we consider them as prime numbers and composite numbers, right? We have learned this, right? Composite number is like 4, 6, 8, 9, 10. All of these are composite numbers, right? Because they can be formed using other prime numbers, and prime numbers are those which we cannot form using anything. So 2, 3, 5, 7, 11, they are like atomic numbers. They cannot be split into anything more other fundamental numbers, right? So that is what we had seen it. But all of these together form the natural number, right? And what is the total number of primes? Can anybody say how many total primes are there? Is it like 100, 1000, 1 million?
95.
95? No, I'm saying all prime numbers. I'm not asking one particular prime number. Total, how many prime numbers exist in the universe? They themselves are infinite. There is no fixed number. There is nothing, because after there is no such thing as the last prime number. After that, you will always find another one. After that, you will find always another. Similarly, composite numbers also, and composite numbers is even easier. 2, 4, 6, 8, 10, all of these are composite numbers because all they are divisible by 2. There are other numbers like 9, etc. Those are also composite, but just you consider even numbers also. They are also how many? They are also infinite. because there is no end to them. And odd numbers, they are also infinite because there is no final odd number, right? So but what can we, so everything infinite? Now what we will do is, it is not, everything is still not infinite. Just 1 second. So we will try to see what kind of infinities exist and what thing. So let me stop. I will start a whiteboard share. Okay. Whiteboard share. Can you see the whiteboard? All of you, can you see the whiteboard?
Yes, sir.
So let us just start putting. Okay. So first we said that all natural numbers, and we said that 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and it will go on like this, right? It will go on, it will never stop. Okay. Now then we said prime numbers. Prime numbers are like 2, 3, 5, 7, 11, 13, 17, 19, 23, then what, 29, then 31, then, and it goes on, right? It goes on. It also does not stop anytime, right? Let me extend it all. Then there are also composite numbers, right? 2, 4, then what, 6, 8, 9, 10, 12, 14, 15, 16, 18, 20, 21, 22, and they go on like this, right? They are all composite numbers. There are also simpler numbers, 1, 3, 5, 7, 9, 11, all the odd numbers, and also all the even numbers, right? Each of these is infinite. There is no final thing that is there for each of these, right? So then question comes is whether all these infinites are equal, or one infinite is bigger than the other. What do you think? So finally we get this symbol here. So what we put after this is this symbol, we put it, right? Infinity. This is just to show that there is no particular number, anything after this. Right? So this is what we say. Okay, Madhura is also joined. And we say, okay, it is infinite, right? So natural numbers, they are infinite. Prime numbers, they are also infinite. Composite numbers, they are also infinite. Odd numbers, infinite. Even numbers also infinite, right? Okay, what do you think is, which is larger than, is there anything larger than one infinity is larger than the other?
Sorry, sir, I joined late. What are we discussing?
We are discussing about infinity.
Okay.
So we are starting with the whatever natural numbers, and then various kinds of natural numbers, and we find that each one of them is infinite. Like natural numbers themselves, starting with 0, 1, 2, 3, they are infinite. Yeah. Prime numbers are also infinite. Even numbers, composite numbers are also infinite. Odd numbers, even numbers, each one of them is infinite, right? See, one way to think of it would be, and I'll tell you 2, 3 mathematical. One way to think of it would be the total number of natural numbers is twice the total number of even numbers, right? You can say, so the natural numbers, which is like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, it is twice the total number of even numbers. And why we say that? Because even numbers is only, every alternate number is even, right? So if you take up 1 up to 10 natural numbers, there are 10 natural, but there are 5 odd numbers, 5 even numbers. If you go up to 100, then there will be 50 odd and 50 even numbers. Okay, so one way to think will be that, oh, total numbers of natural numbers are infinite, but they are twice as much as odd and even numbers, right? And logically it is okay, right? Does it make sense? Do you think that odd and even numbers are half of the total natural numbers?
Yes.
It looks logical, right? It is logical in one sense. Okay, it is logical. And then if you see the composite numbers, it is also, it is actually slightly between the odd and the even numbers, slightly more than the even numbers, because there are some odd numbers also. All even numbers are anyway composite. 2, 4, 6, 8, 10, 12, you can see it. But in addition, there are some odd numbers are also composite. So 9, 15, etc. So maybe they are slightly more than half the natural numbers. Odd numbers and even numbers are exactly half of the natural numbers. And composite numbers are slightly more than half. And if you consider prime numbers, they are very few actually, because the ratio keeps falling. In the first 10 first 10 positive numbers, there are 4 of them are prime: 2, 3, 5, and 7. Okay, 10 to 20 also there are 5, 11, 13, 17, 19. But then it becomes only 2, 23, 29. Then it becomes again only 2, 31 and 37. And then it becomes 43 and 47, I think, right? 43 and 47. And then it is 53 and 59. And then it becomes even lesser and lesser. As you go further ahead, sometimes it will be only one number will be there in a set of 10 numbers. And after that, it might become, for some good thing, it will be even lesser, right? So it keeps giving. So it is much lesser. So you can say that prime numbers are much less than the natural numbers, right? But the way mathematicians think, so they have thought of many on this many times, and then they have got a refined thing. In fact, you know who was the first mathematician to really think in terms of infinities? Was an Indian mathematician, Jain mathematician in 4th century before Christ. Okay, so it is like, maybe it is, now we are in the 21st century after Christ and 4 centuries before. So it is like 2500 years before us. Okay, or 2400 years before us. Okay, he was named as Surya. I forgot his name. Surya someone, and he has given actually 5 types of infinities. Okay, 5 types of infinities, and we will learn about it. He said that one type of infinity is in one direction. Okay, this is what we call it as natural numbers, because they start with 0. There is a starting point, right? Actually, whole numbers, natural numbers start with 1, whole numbers start with 0. But for in any case, there is a definite starting point. There is nothing. You can always say that the smallest natural number, you can always say, is 1. Smallest whole number is 0. You cannot say which is the largest natural number, because in that direction, so if you look at it 0, 1, 2, 3, and you keep going to the right, then on the right side it is infinite. On the left side it is not infinite, right? So this he gave it as the first type of infinity. Okay, but then he said this is only one type. Then he said this is like a line, right? All these numbers are like on a line. You can put it on a line. You can mark the numbers 0, 1, like in a ruler. You have the numbers marked, right? 0, 1, 2, 3, 4, 5. It starts with 0. We don't have rulers going up to negative, but we know that negative numbers exist, right? Which are called as integers. I mean, integers consist of both negative and positive numbers, right? So you if you consider integers, then it is not like, so it is like maybe -3, -2, -1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on, right? So these are, but on the other side also, it is not just -3 is not the last one. You can always say -4, -4, and beyond this there will be -5, and beyond -5 there will be -6, and beyond -6 there will be -7, right? So this also goes on and on. Is there any maximum negative number that you can think of? Is there something beyond which there is no negative number? No. Sai Pranav?
No.
Just as you have positive infinity, there is also negative infinity, right? Because negative also can go to minus 1000, minus 10,000, minus 1 million, minus 56 million, minus 120 million, 1 billion, 1 trillion. You can go on and on and on, right? So this he called it as the second type of infinity. So integers are also infinite, but they are infinite in two directions, right? These natural numbers are infinite. Natural numbers, primes, odds, even, they're all infinite only in one direction. But integers are infinite in two directions, both sides, right? Smaller side and bigger side also, and both sides it is infinite. So this is the second type of infinity, he said. Then he said that while you are thinking of a line, all these numbers we can consist of put it on a line. Even on the ground, if you draw a line, you can mark out 1 0, and one side you can put all these 1 2 3 4. The other side you can put -1, -2, -3, -4, etc. So it will form a line, right? It will form like a straight line. But on the ground, you are also possible. So not only can you draw a line like this and put numbers on it, but then on the ground you can actually, it's an area, so you can also put a perpendicular line to it and start going on the other side, not just on the line, but to the left and right of the line also you can go. So entire area you can cover, right? Entire area you can cover, right? This all of these areas actually they correspond to numbers, and in number theory they are called as complex numbers. Okay, so they have a part, so they have to be represented on a plane. And then he said on plane also you can go to infinite, because you can go not only on the direction north south, but you can east west also, and somewhere in between northeast northwest also you can keep on going in any direction, and it is infinite. So this he called it as the third type of infinity. In mathematics it is like mathematical terms, it is like complex numbers. Then he said that it is not just on the ground, okay, but you can also rise up. See, ground is like flat thing, right? You can only, it is like ants crawling. Let us say ants are crawling, they can only crawl on the ground in this x direction or y direction, right? Like the two lines that I've said, they cannot jump up or they cannot fly, right? But humans can jump up. Animals, there are some animals which can jump, and then birds can also fly, right? So they are in the third dimension. So they are not just crawling on the ground, but they are flying, and they can fly at various heights. So this he thought was the fourth type of infinity. So first we thought in one line in one direction. Then he said in second direction on a line, then on a plane, and then in three dimensions also you can go in any direction in space. You can imagine that from Earth, if you imagine in space, right? One side is sun, one side might be moon. There are some stars on the north side, some on the west side, south side, and wherever in all directions there are stars and constellations, and you can go in any direction. So that, and all those directions are infinite, right? There is no finite some end to it. So this he put it as the fourth type of infinity. Okay. And then he speculated, he said that, oh, I can only think of all of these things, this is what I see, but there might be other beings which can experience even one more kind of thing beyond it, and this he called as infinitely infinite. So his first order of infinity, second order, third order is plane, fourth order is three dimensional. Then he said that there may be other dimensions that I cannot feel or I cannot think, but somebody else might be able to feel, or some other animal or an intelligent being or God might be able to. So he called that as the fifth dimension and fifth way of infinite. Okay, so this is what he thought. I'm just telling you because it is important. He was an Indian mathematician, right? So I think Surya Prajapati was his name. Okay, and he was there in the 4th century BC. And all these mathematical concepts are valid even in today's world. So those things, they have been mapped to corresponding thing, but they are all very valid things. Okay, but now we will look at another way of looking at these mathematical numbers, and which is how mathematicians look at it. Okay, so how mathematicians look at it, let me take a thing and put it thing. So they consider there are some numbers are countable and uncountable. Have you come across this? Countable numbers and uncountable numbers. Countable numbers is everything that we just now saw, right? From minus 50, minus 60, all the way going up to all these natural numbers, whole numbers, they are all countable numbers. You can hear me? Right? They are countable numbers, and because you can put them in order, okay, you can put them in definitely order and there is no gap in between them. Okay, so between 2 and 3, if you consider as a whole numbers or integers, is there anything in between? Between 2 and 3 as an integer, right? Integer, there is no integer between 2 and 3. 2, then next comes 3, next comes 4. So it is very definite by definition, right? They are definite. There is nothing in between. But if you consider the real numbers, right? So countable numbers are like all natural numbers, whole numbers, and integers. They are all countable numbers. And so between two numbers between any two, what are countable numbers? Between any two countable numbers, there is a fixed number of other numbers in between. See, between 2 and 10, if you consider, there are 7 other numbers in between: 3, 4, 5, 6, 7, 8, 9. Then one side is 2, one side is 10, and exactly 7 numbers lie between it, right? So these can be counted exactly how many. Okay, and that's why they are called as countable numbers. What are uncountable numbers? The moment you go into decimal numbers, right? Say, and all kinds of decimal numbers, then they become uncountable. Because can you, for example, between 1.23 and 1.34, how many other what do you call decimal numbers lie between them? Can you tell? Between 1.23 and 1.34, is there a definite number or that is indefinite? It is indefinite, because you can, for example, you can say that between I will write it down as 1.23, 1.24, 1.25, and like this, and I will reach 1.334. Okay, but this is not just true, because between 1.23 and 1.24, I can always write 1.231, 1.232, 1.233, and all the way up to 1.239, and then I can write 1.24. Not only that, between 1.231 and 1.232, I can always write 1.2311 and 1.2312 and 1.2313, and like this up to 10 numbers I will write, and then it will become 1.23, right? And then beyond this, between this, I can write 1.23111, 1.23112, 1.23113. So like this. So if you consider, and these are all decimal numbers, right? These are all decimal numbers, right? So between 1.23 and 1.34 also there are infinite number of other decimal numbers. Not only that, between 1.23 and 1.231 also there are, because this is nothing but 0. Between these two also you consider any two numbers, you consider any two decimal numbers you consider. Okay, between them there are infinite number of other decimal numbers, because I can always write as 1.2301, 1.2302, 1.2303, like this. And between these two, again, if you consider, there are again infinite number of, right? 1.2301 and 1.2302 also there are infinite number of other decimals between them. So this goes on and on, right? So this is a completely different kind of infinity. Till now what we were dealing with is prime numbers, even numbers, odd numbers. They were all countable because we could count them. Okay, but these decimal numbers, we cannot count them definitely. I mean, there can be as many as you can write down, and I can even write something like 1.23000000000567, 1.23000000000578, and between them also I can still further write down more, right? 1.230000000568, right? And between them, so I can go on and on and on. There is no end to it, right? So that is why these infinite are called as uncountable infinites. Okay, uncountable, at least. So do you understand now the difference between countable and uncountable? Countable is very definite. Uncountable is, there is no particular way that you can do this. Okay, so with this, then mathematicians thought that how can we now think of which infinity is bigger, which infinity is smaller. So they kept on thinking. Then there is one conception, and which is useful and which is what is used in mathematics. Okay, so they consider numbers in terms of sets. Set is nothing but everything, all the possible things are there, you put together, and that is like a set. For example, if you are playing Scrabble, at the beginning all those letter things are there, right? Those what do you call those plastic squares with the letters, they are there in a bag or whatever, right? So that is called as a set. That is the starting set of all the letters for Scrabble. Or if you are playing some other game like this, there may be like this. But like this, you think in terms of sets. It is like, or maybe some lottery is there with all the numbers are there. They are put them in a big whatever, that big vessel or a big globe. They put it and then they choose it, right? So what is that set? That set is all the numbers that are contained inside it is a set. So they think in terms of sets. So there is a set of natural numbers, which is like 1, 2, 3, 4, 5, 6, all the way up to infinity. Set of similarly whole numbers, set of thing, and which set is higher. They don't say that the set of natural numbers is higher than the set of or is higher than the set of prime numbers or odd numbers. The way you define it, how do you say one set is bigger, is you check the sets. So let us put it, set of even numbers. Okay, it is 2, 4, 6, 8, 10, and so on. And what is the set of natural numbers? 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on. Right? Now, you say that once, first of all, you say that two sets are equal in terms of content. Okay, not exactly thing, but in terms of the number of elements, they are considered equal. If for every element within one set, you can find one corresponding element in the other set. For example, if we take natural number 1, okay, I can always find one particular number in the set of even numbers, which is 2. Okay, if I take natural number 2, I can always find another next next even number, which is 4. If I take a natural number 3, then I can get 6, right? So every natural number, if I put them in order, first natural number, I can get one first even number. Second natural number, I can get a second even number. In fact, I can get them very simply by just doubling them, right? 3 multiplied by 2, I get 6. 4 multiplied by 2, I get 8. So like this, for every natural number, there is one even number, right? And this is true no matter how far you go. Yeah, 100th natural number, the even number will be 200. 200th natural number, which is 200, the 200th even number will be 400, right? That will go on, but doesn't matter, they may not be equal, but for every one there is a corresponding one. Okay, every one here, there is a corresponding one there, right? And that is why these sets are called as equal. Okay, they are equal, they are not more and things. So in set theory, they are called as equal. So similarly for odd numbers, for every natural number we can find one odd number, and hence the total number of odd numbers is actually, in terms of infinity, it is same as the total number of natural numbers. Not only that, we can think of even the set of all squares, perfect squares. What are the perfect squares? 1, 4, 9, 16, 25, 36, 49. These are all squares. But again, you can find them that corresponding to every natural number, there is a square. 1 is 1, 2 is 4, 3 it is 9, 4 it is 16, 5 it is 25, 6 it is 36, right? So we can always map every natural number to a specific perfect square number, and hence the total number of all of these things is still same. Infinite is same. Not only that, integers also we say that it is same. Okay, integers is the total number of the set of integers In terms of infinity, they are same as the set of natural numbers, because every integer, even minus 53, you can always map it to 53, right? And then put a minus sign to it, right? Minus 67. Yeah, it is actually 67 with a minus sign, right? So you can always map it to one particular natural number, right? So these are called as that's in terms of magnitude of infinity, they are at the same magnitude. Okay, it is granted that for every even number there are two natural numbers inside, but in terms of infinity they are similar. Okay, they are not different. But when we come to these numbers that we talked about, decimal numbers, they are not countable, they are uncountable. So that is the next level of infinity that they are called. So there are actually in mathematics there are different kinds of infinities, I told you. So first level of infinity is all these numbers which are going in both directions, right? Integers going in both directions, like a line, right? The numbers which are going on one line, and we have marked out the we have marked out the numbers. Here there is one, here there is one, here there is one. So these are like maybe whatever. This may be 0, this may be 1, this may be 2, this may be 3, and -1, -2. These are all marked, and both directions they are called as first level of infinity. The next level of infinity comes when you are talking that between any two numbers there are, as I said, there are so many decimal numbers, and between any two decimal numbers so many other decimal numbers, right? This goes on and on. So even between any two, so what I wanted to say is there is a set of numbers which may be infinite, but between any two they are finite. Okay, so that is the first level of infinity, they are called as. But there are others which between any two also, there are other decimal numbers. You take it between any two of them, there are again infinite decimal numbers. Here there are finite, but here there are infinite if you consider the decimal. So this is the second level of infinity. Okay, and like this there are third level, fourth level, and fifth level of infinity. So it's very interesting. It is actually just to know and think about it. So I thought I will introduce you to this topic, and there are a lot of interesting theorems, but it's kind of abstract, but it is very useful to know and then start mapping. Okay, any questions? Any questions?
No, sir.
What other infinities can you think of? What other infinities can you think of? We are only thinking of numbers, but there are no such, there are so many other things in life that can also be infinite. Can you think of any other thing? Madhura, can you think of some other things? Or Sai Pranav or Avnish? Anybody?
Sir, I don't have any questions.
No, not questions. I'm thinking any other things that you can think of as infinite. See, I will look at it as English language words. They are finite. Yeah, in a sense they are finite, but we are always adding some more words to it as we continue, right? There were some, see, for example, 100 years back, there was no word called as computer, binary. Binary was there, but hexadecimal, we say, and so many bit, byte, megabyte, kilobyte, Mbps. All of these words were never there, right? But they got introduced as we invented so many things, and then chromosomes, and then DNA, and whatever it is in biology, so many things we invented. Physics, so many things. Every time you invent something new or whatever it is, and not only in sciences, but even in arts and culture, also new different concepts you think, then you have to form words for it, and then new words come into existence, right? So
I would think words are infinite.
huh?
I would think words are infinite.
Yeah, words will tend to be infinite. At any given point of time, they may be finite. You can say that, okay, whatever is there in Oxford Dictionary, that is it. But next year's Oxford Dictionary will probably have a few more words. Every year, if you see, they will say, oh, we have added these many words to the Oxford Dictionary or Cambridge Dictionary also, right? So that way, the words themselves are infinite. But then if you say sentences or phrases are formed from other words, right? You combine different, oh, go here, come there, come on, let's play cricket,
Then I have a question. So like if you have a Rubik's Cube, then are there a finite or infinite solutions to the Rubik's Cube?
There are finite solutions because it has got a finite number of combinations, right? There are only so many faces, so many squares within each face. Everything is finite. So from finite, if you do any operation, if you do finite operation, you will only get finite.
Okay. And so what about chess?
Chess also, it is actually finite. It is very large, but it is finite. It is extremely large, but it is not infinite. And why? Because finally chess mein what happens is, finally some pieces will get killed. At some point, some pawns will get captured, pieces will get captured, and it reduces. And slowly it never increases, right? See, there are, at starting point, there are 32 men on the chessboard. 16 from white side, 16 from black side. You cannot have a 33rd piece on the board. It can only be less than 32. After some pawns get exchanged, pieces get killed, 32 will become 31, 30. And finally, at the least, it can be 2 because 2 kings are left. It can be anything somewhere between 2 and 32. So whatever you do, there are so many ways. It is very large, but it is finite. It might be more than the number of atoms in the universe, the total number of chess games, but it is still finite. It is not infinite. Very good question, Saifram. Okay. This is the way we have to think. Okay. Okay. So I think with that, we are ending our session today. I'm stopping the recording. Please think.